Hey, so we're going to go over some of the problems from the um, divisionals that was on the weekend. We'll start by going over what was probably the hardest problem, which is J. I'll just share my screen. The problems are on a website. If you go to Divisional Debrief, and you can click the link to the problems there. And then if we go down to J. Where is it? So just a quick refresher on the problem. So in this problem, the first part isn't that. It starts to become useful after the bit that I highlighted. So a blog post is considered juicy if it contains any substring on a buzzword list. So as an example, if the buzzword list is South Pacific, regional, and contest, then the blog post Jeremy loves fish and South with some extra letters added to it, they're not juicy because neither of them contain a buzzword as a substring. So substring has to be like continuous. Whereas Jeremy loves programming on the beach is juicy because programming is a substring here and programming is one of the buzzwords. So any string that contains some number of buzzwords, whether that's one buzzword or more than one, is considered juicy. So Jeremy wants to stop making juicy posts because he's keep making all these juicy posts. And so his manager's forcing him to write a juicy story that has exactly K characters. The question is, how many non-juicy posts of length K are there? Where a post must be a sequence of lowercase letters. So you're given N, which is the number of buzzwords, and K, the length of the blog post, and then you're given all the buzzwords. So perhaps interestingly, the bounds, so N, the number of buzzwords, is up to 100. Also, the sum of the lengths of all the buzzwords is from 1 to 100. So the buzzwords and their total length is quite small, but K, which is the length of the post that you need to make, is very large, up to 10 to the 18, which interesting bounds. So this kind of says that, well, we want to have a solution which has could be a slow complexity in terms of N, but a very fast complexity in terms of K, because anything like linear in K or even square root in K is going to be way too slow. And you output the number of non-juicy posts of length K and output it modulo 10 to the 9 plus 7, like this. So I'm going to present the solution. And if anyone who's here has any questions or comments, just type them in the chat. So the examples here are not very good to go over. The first one, they give you got to make a length 3 word, and it can't contain any of these 3 as substrings. Well, I guess to work out the total number of length 3 posts, including juicy ones, is just 26 to the power of 3, because there's 26 choices for each letter. This is 17,576. Now, there are 3 buzzwords, all of them are length 3. So the only posts that are juicy are precisely exactly equal to the buzzwords. So there are 3 juicy posts. So minus 3 to get the number of non-juicy posts, which equals this number here. So that one's pretty easy to work out by hand. This second example, I'm not going to go over by hand because there are so many possible answers. And so we'll definitely need an efficient solution to compute them. Even in this example, so the length of the post is 10. 26 to the power of 10 is already about 10 to the power of 14. 1.4 times 10 to the power of 14. So even at this point, you've reached way too many. You can't go over them all by hand. There's way too many of them. So we need some sort of efficient way to do it. And so the first kind of thing on doing this problem is, well, you have these different non-juicy, or there's different buzzwords. So you have the list of buzzwords, and you need a string that contains no buzzwords in it. So if a buzzword is programming, or just program, you can't have program in it, but you can have like prog or progra, but you can't have program. So we might want to have like a DP solution. And if let's consider a DP solution where you want to build up your string one character at a time. So you currently have your state could be the length of the string, and the answer is how many buzzwords of, or how many say the length, and how many strings are there that start with this length, and the rest of the K characters are filled with letters and don't have any buzzwords. So the state is the length you've already filled so far, the length you've chosen so far. So the number of characters in your string so far, you're adding one character at a time, and your answer is the number of possible non-juicy posts. But this state isn't sufficient because the previous letters matter. And in fact, if you're adding letters one at a time to the end, so we've got to, let's say our post so far is prog. Well, what you care about is whether the next letter you add will contribute to a buzzword or not. And so to do that, you want to know, well, what prefix, what suffix of our string so far. So if your post so far is like, I love prog, and you're adding one more letter to the end, like an R, well, you care about whether this R either finishes a buzzword or could lead to us finishing a buzzword in the future. And if the buzzwords are, in the example, they are South Pacific and programming and contest, then adding an R to the end here, the only buzzword that could help produce is programming, because that's the only buzzword we've started creating. And to work out what buzzwords we've started creating, we want to consider a suffix of our post so far, so suffix being in the end. Is this suffix a prefix of any of the buzzwords? So prog R is a prefix of programming. And so potentially this could lead to a buzzword being created if we later add like amming to the end. And so in creating strings, we want to know, well, what suffix of our word is a prefix of a buzzword? But it's possible that there could be multiple suffixes of our word that are prefixes of buzzwords. So if the buzzwords are, if your string is, for example, like A, B, C, D, E is your string so far, and the buzzwords are like D, E, F, G is a buzzword, and B, C, D, E, Z is also a buzzword, then DE is a prefix of this one here. And so it's possible that if you added an F and a G, then you'd make a juicy post. Alternatively, BCDE is a prefix of the second buzzword. And so if we added a Z to the end, we would make a juicy post. However, notice that if we keep track of the biggest suffix that is a prefix of a buzzword, so to keep track of, well, BCDE is the biggest suffix of our post so far, which is a prefix of a buzzword, then BCDE contains DE within it. So if we just store, well, our buzzword ends with, our post ends with BCDE, then we know if we add a Z to the end, that's bad. But we also know if we add a F and a G to the end, that's also bad, because by knowing that our post ends with BCDE, we know then that it ends in DE, because that's part of BCDE. So we need to keep track of, if we're building up our post one letter at a time, the two things that matter are two things matter. The first one is the length of our post. Oh, sorry, I'll scroll down. The first one that matters is the length. So let's go to blank page. One, we care about the length because we want to have a post of exactly length k, but also the longest suffix of our post so far that is a prefix of a buzzword. So we can have a DP where these two things are our state. Now the second one's a bit weird. The longest suffix of our post is a prefix of a buzzword. To do that, let's consider every possible prefix of a buzzword. So if our buzzwords are, let's go with the example of like South and Pacific. And also let's say so is also, these are 3 buzzwords. Then all the possible prefixes of buzzwords in green, S, SO, SOU, SOUT, SOUTH, and then P, etc. Finally, we have S and SO again, but these are repeats, so we can ignore these. We just want to know how many different possible prefixes of buzzwords are there. And we've listed them all out in this example. But remember from the problem had the constraint that the number of keywords, the number of buzzwords, some of their links was at most 100. And so then the number of prefixes is at most 100. So there's at most 100 prefixes. And to work out all of the prefixes, we could just use the for loop, add them one by one to some sort of array, and then remove duplicates. And then we have a list of all the possible prefixes of buzzwords. So our DP state is the length. And which one of these prefixes is a suffix of our post so far, but also want to add the empty string as well, because it's possible that if our post ends with, for example, a Z, then none of these are going to be suffixes. So we add like the empty string. Just going to put like close quotes, the empty string as a possible suffix. So DP length, and then the longest suffix that is a prefix of a buzzword. And if we number all of these, we number them like 0, 1, 2, 3, 4, etc., then we can store it as a number. So our state is the length and the longest suffix of our, that is a prefix. This is our DP state. And then our recurrence would be, well, consider adding every possible letter. So recurrence, add one letter, calculate the new biggest prefix, so add one letter, calculate the new biggest prefix, check that prefix doesn't complete a word, the new biggest suffix, sorry, that is a prefix of a buzzword. Then just check that this prefix isn't in fact a complete buzzword, because if it is, then we have a juicy post. We want non-juicy posts. And then add DP of length +1 and this new biggest suffix as to our answer. So this is a DP, and the complexity, well, there's order n times 100 states, where 100 is the total length. And the recurrence, well, is order, there are 26 letters, but also each time we add a new letter, we're going to look through all our prefixes to work out which prefix is the matching one. So we're going to have 26 times 100 recurrence. So the complexity is order like n multiplied by 260,000, I think, something like that. 100 times 100 times 26. Yeah, 260,000. This is our overall complexity of this solution. Unfortunately, this is way too slow. Where n, by n I mean k. The length of the string is k, not n. Sorry, k. Now this is way too slow because k is up to 10 to the power of 18. So this solution is going to be way too slow, but it's a good starting point. So we're going to have to improve upon this solution. And to give myself some more space, I'm going to just share a new screen, which I can write more all over. I have to keep erasing it. All right, you should be able to see my iPad screen now. So we have this here. So far we have, so far we have an order like k times 260,000 solution, which is too slow, like way too slow. So we want to improve upon this. And we're going to have to do quite a, I guess, a novel idea. And that idea is, well, we're going to use a form of matrix multiplication. And to do that, we're going to compress our state a bit. We're going to come up with, in fact, a new state. So our DP state will instead consider both the start of our word, the start of our blog post, and also the end of our blog post, and also its length. So imagine we have, what our matrix is going to look like is along the side here, we're going to have the very start of our post with all the buzzwords. So if the buzzwords and their prefixes. So if the buzzwords are like A, B, C, and well, let's say the buzzwords are A, B, and C, D, then the prefixes are the empty prefix A, B, C, and C, D. So we put all of these as rows in our matrix. So we have A, B, C, C, D. So we're going to have 5 rows like this. Let me draw a bit nicer. Draw in the matrix in blue. We're going to have 5 rows, and also going to have 5 columns to correspond to the same thing. 1, 2, 3, 4, 5. Not the best drawn one, but that should suffice. We're going to imagine we add 1 letter to the end. So we start with this, with one of these things being our post. So let's say we start with AB being a post. And then imagine we add 1 letter to the end. Let's say we add an A to the end. Well, what's the new biggest prefix? It's a suffix. It's just A here, because we started with AB and then we went to ABA. Now the biggest suffix of ABA, that is a prefix of one of these buzzwords, well, that's going to just be, in fact, let's not start with AB because AB is not allowed because we're starting with a buzzword. Let's say we start with, I'm going to say modify my example actually, sorry. I'm going to change it. We have ABC and also CD as our buzzwords. So we have AB, ABC, C, and D. So to add another row, another column. Like this, just to make my example a bit nicer. So let's say we're starting with just A on its own. So imagine our post starts with just A on its own. And let's say we add the letter B to the end. What's the new biggest suffix of this? That's a prefix of a buzzword. Well, all our prefixes are listed up here in a different color to make them obvious. They're in green up here. Well, it's going to be just AB, the entire thing, because this entire thing is a new prefix of a buzzword. Now, what if we had A, B, and we had A, and then we added an A on the end? So we got AA. Well, then the biggest suffix of the prefix of buzzword would just be A on its own still. What if we had A and we added a C to the end? Then C would be the biggest suffix that's a prefix of a buzzword. And if we had A and we added a D to it, like this, so we added a D, then no suffix of this is a prefix of a buzzword. And so the answer would be the empty string. And so what we're going to represent in our matrix, we're going to have the same values here along the columns. The value in, let's say, for example, this cell here is the number of ways to add one character to A, the row, so that the biggest suffix that is a prefix is AB. And there's one way to do that in this case. The only way is if we add a B to the end. So we're going to put a 1 here. What about A to ABC? Well, it's 0. There's no way to add one character to A so that ABC is now a suffix of it. What about A to C? Well, there's one way. We just add, this meant to be CD, not C. We just add a C to the end. What about CD? There's no way of doing that. What about A? Well, there's one way of doing that. We just add an A. Now, what about A to blank? Well, in fact, there's going to be 23 ways of doing this. That's just the 26 remaining letters. So all the letters except A, B, and C. Okay, we can fill in the rest of the matrix. So what about AB to blank? Well, what about AB to A? There's one way, we add an A. What about AB to AB? Well, there's no way to add one character to AB so that the biggest suffix is still AB, so that's 0. AB to ABC, I'm going to put a 1 in there for now, but then we're going to remove that later, but I'll explain why. What about AB to C? In fact, there's 0 ways to do this, because even though we put a C on the end, we get ABC. C is a suffix, but the biggest suffix that's a prefix of a buzzword is the complete ABC. And AB to CD is going to be 0. And then the remaining ones, it's going to be 24 here. And we could fill in the rest. So blank to A would be 1, 0, 0, 1, 0, and 24, for example. ABC, and like C to everything would be 1, C to A is 1, 0, 0, 1, 1, so 23 here, and so on. Now, the reason why I put the 1 in pink here is I'm going to modify it a bit so that we only put numbers if the resulting string we create is not juicy. So not juicy, remember, means doesn't contain a buzzword as a suffix. So in this example, the buzzwords are A, B, C, and C, D. And so if A, B, C was a suffix, then we have juicy post. So we're going to put 0 here instead because of that. And as a result, then anything ending in ABC also has zeros, because there is no way to add one character to ABC so that it's no longer juicy. Like once it's juicy, it's always juicy. And same with CD. So we're gonna have all zeros here, like this. So we're gonna create this matrix in this way. Now, computationally, how we do this is not too hard. It's just, we can kind of brute force it. We can just brute force our creation by just in each cell, we start with AB, we try adding each individual letter, and we check whether the biggest suffix is then AB. We'll just do the same thing for every pair. It might be slow, but because there's at most 100 suffixes, even if we go for each cell, so complexity of creating this, well, there's 100 prefixes, so 100 rows times 100 columns times 26. And then we're going to check, we're going to find the biggest prefix, which we're going to add times 100 and then check what word it is. We'll add times 100 for that. Even in this case, our complexity is only like 26 million, which is fast enough to do because the time limit is 5 seconds. And so you can essentially brute force the creation of this matrix. And there are more efficient ways of doing this, but they're not really required. You could do like a data structure, like a trie, also known as a prefix tree. That might help you, but in fact, it's not required. And so why have we created this matrix is perhaps an interesting question. How are we going to use this? Well, this matrix tells us what happens when we add one letter. Is it juicy or not? Perhaps an interesting, not very useful, but kind of interesting observation is if we take this first row here and we sum all the entries, that will give us the number of length 1 non-juicy posts. In this case, it's 26 because every length 1 post is non-juicy. Now, why is that the case? Well, if we start at a blank, then the sum of all these entries in every column for the first row, that's going to be, well, it's going to be 1 for every length 1 prefix, and every remaining character will be in the first column, unless if there are any length 1 buzzwords, we're going to put a 0 there because we put 0 in columns corresponding to the buzzwords. And so as a result, the sum of this first row is the number of length 1 non-juicy posts, which I guess means if k equals 1, we've solved the problem in a very convoluted way. But we want to use this to solve the problem. Let's say we want to make a new matrix, which is the same thing. So we're going to copy and paste this matrix. Copy and paste below. Except the difference now is that we want our entries to correspond to what if we add 2 characters to the end. So let's just erase all of these. Erase everything. Like this, okay? So this first matrix was what if we add 1 character. In our second matrix, it's going to be what if we add 2 characters. And by that I mean this entry here, for example, like this entry that I put dot in, will be the number of ways to start with blank, add 2 characters, and have the longest prefix, the longest suffix, sorry, the longest suffix, you can put in the rest, the longest suffix, that is a prefix of a buzzword, BAB. And there's obviously one way to do that. We just add A and we add B. Also implicit in here, we're ignoring any juicy words. So there's only a number of ways to do this that also results in a not juicy string. For AB, there's one way of doing it. What about for just A? Well, for just A, there's 26 ways to do the first character and then one way to the second one. So there's 26 options here. What about ABC? Well, again, this entire row, this entire thing is going to be zeros because ABC is a juicy word. What about C? Well, there's 26 options here. And CD, one option. For blank, well, for blank, it's going to be 26 times 26 minus everything we've already covered here. So 26 times 26 minus, minus 26 times 26 minus 26 minus 1 minus 26 minus 1, which will get us, I think if I'm right, 622, if I've done my maths right. And in fact, we're going to put a 0 here at CD because, again, this entire column will be zeros. So I think this is correct for the first row. I could be wrong. But it's a bit hard to compute. But can we, so look at this here. Can we use our first matrix to compute the second matrix? Well, let's consider this position, this position here. The number, so the very top left corner, the number of ways to start with nothing, end with no suffix, and add 2 characters. Well, let's use this first matrix as an intermediary because we're adding 2 characters. Adding 2 characters is adding 1 character twice. So this will just be here, the number of ways of adding 1 character. So if we start with blank and finish with a prefix of X, and then start with X and finish with a prefix of the empty prefix, and we multiply these values together, then we're going to get the number of ways of starting with blank and ending with blank and having X in the middle. Because this says the number of ways to start with blank and end with X. Let's say X is B, for example. Number of ways to start with blank, end with B, and adding 1 character. And then to add our second character, we start with B and end with blank and add 1 character like this. Then that'll be the number of ways to start with blank, end with blank, and have a B as one of the characters in the middle. And if we do this for every character, so we sum this value for every character, we're going to get our 622 in here. So what does that look like? Well, for A, it's going to be like blank followed by A, which is this, multiplied by A followed by blank. That's this here. So we're going to have 23 times 1. Let's move this. Then we're going to add, what about B? Well, for B, we're going to have, blank followed by B. Well, that's actually not an option. Sorry, blank followed by AB. Blank, we do it for every prefix. So blank followed by AB, there is 0 ways, so ignore it. What about blank followed by C? Blank followed by C, there's 1 way of doing it. So for blank followed by C, it's 1 times C followed by blank. That's 23. So we have 23 ways again. So we have 23 plus 23. Finally, what about we have blank followed by blank, followed by blank. So we have like 24 times 24. And if we add these together, times 24 plus 23 plus 23, we get 622. We get the same value as expected. As another example, let's try computing this value in here, this 26 in here. Well, this will be the number of ways to start with blank and then have A as an intermediary and then go to A again, or to start with blank, have A, B as an intermediary, go to A, start with blank, have blank, go to A, start with blank, have C, go to A, start with blank, have, AB, go to A, or already at AB, like ABC, and every other intermediary. So if we add all of those together, for this first one, we get 0 to A, that's 1, times A to A, that's 1. For the second one, we have 0 to AB, that's 0 times something, doesn't matter. Blank to blank is 24 times blank to A, that's 1. What about C, blank to C to A? Well, blank to C is 1 times C to A equals 1. This is going to be 0 times something at the bottom. We add these together, we get 26, which is the same value we got here. And in fact, for every cell, we're going to get 26. So to compute this 26 value here, we multiplied blank to A. So we multiplied this value blank to A by A to A by this value here. We also modified blank to blank with blank to A. So we multiplied this value times this value. We then multiplied blank to A with A to A, these two together. We then multiplied blank with AB through to A. We then multiplied this value here, with this one here, with this one here, with this one here, and this value here with this value here. And so what's interesting about this is that this looks a lot like matrix multiplication, because we're just multiplying like this times this plus this times this, etc., which is exactly precisely matrix multiplication. So to get the value in this cell down here, we just multiplied this matrix by itself, we squared it, and then took the value in this cell here, because we did this times this plus 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 this times this, which is matrix multiplication. To work out the value here, we did this times itself plus this times this plus like this, etc. Which again, matrix multiplication. And in fact, this whole finding intermediate thing is precisely just matrix multiplication. So if we square this matrix, we get this one, the first matrix, and we square it, we get the second matrix. Okay. Let's say, what happens if we multiply this matrix by this matrix? Well, in that case, we'll get the number of ways to add 3 characters. So we'll get the same matrix, but with 3 characters, which is the same as cubing the first matrix. So if we cube the third matrix, we'll get the number of ways to add 3 characters. If we take the first matrix to the power of 4, we'll get the number of ways to do it by adding 4 characters. Now, if you're unsure how this generalizes to like 2 to 3 to 4, have a think about it, maybe play around with a few examples, and then hopefully it will make sense. But to get this matrix for what if we add X characters for some X, we just take the first matrix to the power of X. So then what happens if we take the first matrix to the power of K? Well, that'll tell us the number of ways. So I'm just going to, again, copy and paste the same matrix again. And assume this third matrix is, so let's call this M1, M2, which is equal to M1 squared. We're going to have MK here. So MK, which is actually in fact equal to M1 to the power of K. And imagine we've populated it with values. Then this cell here, for example, or let's go this one here, we'll sort number ways to start with AB, then add K characters. So we add K characters, not have any juicy, not be juicy, and have our final prefix be just an A. The biggest suffix that is a prefix of a buzzword be A. So this all here represents. Now consider the first row. Then this value here is the number of ways to start with an empty string, add K characters, not be juicy, and have the biggest suffix be the empty string. Then this value here is the number of ways to start with an empty string, add k characters, and have the biggest suffix be just an a, and etc. all the way along here. But if we consider some non-juicy length k string, then the biggest suffix of it, that is a prefix of a buzzword, is going to be one of these values here. Any of these ones here. Could be the empty string A, AB, or C. It couldn't be A, B, C, or C, D, but these values can be 0 anyway. It couldn't be A, B, C, or C, D, because then it would be juicy, but it's going to be one of these one and this one here. And so if we sum the values in these cells, so if we go this value plus this value plus this value plus this value, this will give us precisely the number of non-juicy length k strings. And in fact, we can sum the entire row because we know for a fact these two values are 0. Because we said in any column where the thing is juicy, we're going to have just zeros. Like that. And so we're going to have just zeros here. So if we sum the entire first row, we get the number of non-juicy length k strings, which in fact, if you remember earlier, I said the first row of M1 was number of length 1 non-juicy strings. And the pattern still holds for MK, the number of non-juicy length k strings is just the sum of the first row. So we're almost done. We have a way to compute M1. And we know once we have M1 to the power of k, we have our answer, just sum the first row. So the question is, how do we compute M1 to the power of k, where k is very large, up to 10 to the 18? So the only challenge is how do we take a matrix to a very high power? Because matrix multiplication, if we have an n by n matrix, n times n, matrix multiplication is order n cubed, because if you think about it, 3 nested for loops will do it. So we have an n cubed algorithm for multiplying matrices. Naively, we'd have n cubed times k to multiply a matrix k times. This is way too slow because again, k is up to 10 to the 18. But we can use a trick called fast exponentiation. So fast exponentiation. This trick utilizes the following thing. If we start with m and we take m squared, we get m squared. What about m squared squared? In that case, we get m to the power of 4. What about m to the power of 4 squared? This is m to the power of 8. What about m to the power of 8 squared? This is m to the power of 16. What about m to the power of 16 squared? This is m to the power of 32. And so by doing 1, 2, 3, 4, 5 multiplications, we've got m to the power of 32. And with just one more multiplication, we'll get m to the power of 64. And just one more, we'll get m to the power of 128. So if we just keep squaring, so when we get m to the power of 32 squared, this is m to the power of 64. We just keep squaring, we keep doubling this exponent here. And so if our exponent, so if m to the power of k, if k is a power of 2, then we can compute this in just log k multiplications. Because after log k multiplications, we are done. And so in that case, our complexity is just n cubed log k, which is a lot better. In fact, in this case, n cubed times log k, n is the size of our matrix up to 100. K is 101 technically because the empty string. log k, well, k is up to log k, log 10 to the power of 18. This is log base 2, so that's about 60. So we have 60 times 100 cubed equals 60 million, which is fast enough. So if k is a power of 2, we're done. We have our solution. What if k is not a power of 2? Well, we do a very similar thing, except we can go recursively and work out what multiplications we want to do. So let's say we want to compute m to the power of 50. Well, m to the power of 50 is equal to m to the power of 25 squared. Okay, what's m to the power of 25? Well, this is equal to m to the power of 25 is m to the power of 12 squared times m. Because m to the power of 12 squared is m to the power of 24 times m is m to the power of 25. Then we square this, we get m to the power of 50. Okay, what about m to the power of 12? Well, this is equal to m to the power of 6 squared. So we get m to the power of 6 squared times m squared. What about m to the power of 6? That's m to the power of 3 squared. So we get m to the power of 3 squared, then squared again, then squared again to get 6, 12, 24. So we get 24, 6 to 12, 24. We times m, and then we square it. Then m to the power of 3 is just a new bracket. We get m squared times m. This is m cubed. Then we square it 3 times. We times by m, and we square it. And this result here, if you go in reverse order, this is then equal to m to the 50. Because we just decomposed it one step at a time. 50 is 25 squared. 25 is 12 squared times m. So like 12 squared plus 1. Then to 12 is just 6 squared, like 6 times 2, n to the power of 6 squared. Then n to the power of 6 is n to the power of 3 squared. Keep decomposing it down, and we get this. The benefit of this is we have 1 multiplication, 2 multiplications, 3, 4, 5, 6, 7. We have just 7 multiplications to work out m to the power of 50. And for an even bigger number, like for 100, it would just be 1 more multiplication, just squaring it. And so this procedure will also be log base k multiplications. Why is that? Because each time we half a number, we do up to 2 multiplications, or order log k here. Because to get from 50 to 25, for example, we do 1 multiplication. To get from 25 to 12, we do 2. We first square it, then times m. So we do at most 2 times log multiplications. Now in code, this will look like, let's say we want to multiply, like a function. This works for matrices, also works for integers. Consider it for like, let's say matrices, we have like a function returns a matrix, and the function is called multiply, and takes in, or it's an exponent, sorry, so exp, exponent, like it takes power, or exp confused with either power of, let's just say like power. We take our matrix m, the power of k. This function will look like, we first divide by 2 and round down. So we say the answer is initially the power of m k divided by 2, rounding down. We then square that. So we go ants equals ants times ants. And finally, if m is odd, then we multiply the answer times m. And for our base case, our base case is just if k is 0, then we return the identity matrix like that. Or a different base case, if k is 1, we just return m. Both identities work. Or base cases like this. Yep. So this is called fast exponentiation because it's an order log complexity to multiply matrices or even any number. And of course, the problem asks us to find the answer mod 10 to the 9 plus 7. So we modulo along the way. And so the overall time complexity is log base k times 100 cubed, which is, as I said, fast enough, about 60 million. For a 5-second time limit, this is easily fast enough. So that is the solution to problem J. For anyone who's here, let me know if you have any questions. If not, it looks like we don't. I'll stop my screen share and hand over to someone else to do a different problem.
Since a few people have popped in and out, do we want to ask again which problem to do? I guess we can do the poll again. We can just ask.
Oh, sorry, I'm muted. I'll relaunch the poll.
Or if anyone has some suggestions for a problem, just put it in the chat.
Yeah, actually that works. Actually, yeah, that's easier. If you want to go over any specific problems other than J, obviously, put that in the chat.
Let's do the poll. Just so there's something to.
I mean, the poll had D and E as responses before. If I relaunch it.
I might have picked something. I don't know. I was bored. I might have picked something as well.
Give a minute. Everyone can also have like a break after listening to me talk about one problem for an hour. If not, I'll let you choose what one to go over. So H and M both have requests.
D also has 2.
Oh, okay. Yeah. Oh, I see. Yeah.
Yeah, that was allocated to you. I guess I can do it.
You want to do D? Do you want me to share my screen?
Yeah.
All right, we'll do D then.
It's pretty easy to share the screen. So I can probably just do that.
You do it? Okay. Yep. I'll end the poll.
Since we already went to this. Okay. You can see it, right?
Yep.
All right. So in this problem, there's a bunch of clocks, and I think, are they time zones? Okay, no, it doesn't say that, but it says they're clock relations, and that just means that they have a different offset from a certain time. So yeah, so I guess it's kind of like in the problem, you have a bunch of clocks that are in different time zones, but you're not actually told which time zone they're in. All you're told is that there's certain relations between them. So in particular, we're given a bunch of triplets, X, Y, and D, such that the time zone of clock Y and the time zone of clock X differ by D. It's always confusing me if it's like forwards or backwards, but it doesn't really matter. Just pick one way and stick with it. Yeah, so I guess X will be D seconds bigger than Y at all times. Yeah, there could be multiple X. So yeah, so X and Y are the clocks, D is the offset. And so I think, yeah, so you can interpret this as a graph. So I'll just go through the samples. As much trying to scroll, so it's a random line. Okay, so the first sample, it's like a triangle graph. So 1. So 1 and 2 differ by 3 seconds. I guess I'll draw this directed and write 3 there. 2 and 3. Well, so yeah, these are kind of directed edges. Or you can think of it as 2 to 3 is an edge of +4, and 3 to 2 is an edge of -4. But I'll just do them all positive like this. In the statement, are they all positive? Yeah. So I guess that forces the order of each pair. But it's equivalent. It'll actually be equivalent to saying like 2, 3, 4 will be equivalent to saying 3, 2, -4, if that makes anything clearer. 127. Yeah, so 2, 3, 4 is the same as 2, 3, -4. Okay, so that one. Okay. So you can kind of see that this is consistent because 3 + 4 = 7. So you can think of it as like the time zone of this one is like, say, 10, and this one's 13, and this one is 17. I don't remember the exact setup. Times are kind of confusing, but I think the easiest way is to just reinterpret the problem as each node you have to allocate a number, and you're given a bunch of conditions on the differences between two numbers. It's like 1, 2, 3 means, I guess, the value of 2 is minus the value of 1 is 3. The value of 3, and the second one means the value of 3 minus the value of 2 is 4. And the third one means the value of 3 minus the value of 1 is 7. And so we can see that if we allocate them like this, which is pretty easy to see from our picture, then it worked, I think. And yeah, we output that to say it worked for some reason. And if it's wrong, you say wake up. So I'll do the other case now. So that case, why did I leave it up? Now do it. Nice. So this is very similar case, just one I just changed to 8. And you can see that it's impossible because if this is anything, this is X, then this one is forced to be X + 3, the one at the bottom. And this one is forced to be X + 7 from this edge. It's forced to be X + 7 from that edge because X + 3 + 4 is 7. But from that edge, it's forced to be X + 8. And so we have a contradiction. So this case was impossible. So we output it. We can't do it. Yeah, the last one should be fairly quick as well. So I'll just do it. Even though we probably get the point by now. Oh, there's another one. Okay, that one's a degenerate case, but it's good to know that you can join stuff to itself. So yeah, if something's connected to itself, it's pretty obvious that it has to be 0. All right. Yeah, there could be some edge cases to do with that, but no, not really. Most solutions will deal with it without much thought. So yeah, I'll do the last one in case it's interesting. Okay, it doesn't look very interesting. I guess you just do them all and make sure they add up to the right thing if you pick some. Okay, so hopefully from the first diagram, or the second diagram, the one that's sample number 2, you saw that we could just, like, it's a bunch of stuff that's connected. We can just allocate the first one randomly. It doesn't actually matter what we allocate it to. Because yeah, I guess you can prove it. You can say if there exists a valid arrangement with this value equal to x, then there also exists a valid one where it equals y, because you can just increment everything by the difference. So I guess in a component, it doesn't actually matter like what each value is. All that matters is the relative differences. I guess that's the nature of the problem. So because of that, because the differences matter and the values themselves don't actually matter, what we can do is just kind of arbitrarily allocate a value to some node. So in this case, what we do is just arbitrarily allocate some node in this graph. So like to node 2, we can allocate a value of 1 or something. Doesn't matter what it is. You can even just call it 1. And then from that, you use the graph and you traverse it. You search it using a depth first search or breadth first search, I guess, any search that will access everything in its component to see what the resultant values are forced to be. So in this case, we had an edge from 1 to 2, which is 311. And so if we said if we set 2's value to 1, then 2 minus 1 has to be 311. So this one would have to be negative 310. That's good. Yes, it's negative 310. And so that satisfies that. And then I can do some more. So like 1 to 3. So 3 minus 1 has to be 309. And so that one would have to be 1. And then I won't do 4, but you can check that 3 minus 2 is equal. Oh, what did I do? That should be minus 1. Right? Yeah, because 3 minus 1 is 309. And 3 and 2, their difference is 2, because what's this up? Yeah, it's fine. So yeah, you subtracted them backwards. So 2 minus 3 is negative 1, which is good. Well, the value of 2 minus the value of 3 is 2, which is always 1. Okay. So yeah, you can check it for 4, and you can check that if we just search over this graph, we keep adding the right increments, then we'll do it. I guess that detail about negative values comes in from before. So what is it? I guess it's an implementation detail. When we're implementing this, we want to actually add an edge both ways. So say between this edge and this edge, so 2 to 4, 620, we want to add an edge from 2 to 4. We want to add an edge from 4 to 2, that is 620. We want to add a negative edge the other way, negative 620. Now, the point of this is because you don't actually know in advance which way you're going to traverse the graph, so you should just be prepared for all situations. And so what you do is you DFS, like a regular DFS. I guess someone could be right about because it's file the problem, I guess. DFS of U is going to be, so for each edge from U to V, we want to set the time of V equals time of U plus edge weight. Let's some space. That's the weight of the edge. And then we DFS. And the other thing we need to do is check for contradictions. So what we also do is if time of V was already set, in other words, this was already searched for in another branch of the DFS, then if what it was already set to is not equal to what we're setting it to now, then there's a contradiction. So I won't write the details of that, but basically the two things we have to add to this DFS is obviously if we've seen it before, don't DFS again, because then you'll run into a recursion loop. But also you have to check that there's no contradictions in this step. So you check if V is already seen. Now, this is all good, I think, for all the samples, except for the bottom one, but the bottom one's a bit of a degenerate sample, so I'll ignore it anyway. More interesting case where this is not a full solution is when there's more than one component in the graph. But yeah, it's really easy to deal with that. So I'll just clear, I think. So we dealt with a case where there was like a bunch of stuff, something like that, right? And what our solution was to start at some node and then search from it. So allocate this one randomly and just search from it and make sure we don't hit any contradictions. But there could be some other blob of stuff which we haven't, and there might be a contradiction here, like this case, there might have been a contradiction that we never saw. So what we do is we just make sure we DFS from every single component in the graph. An easy way to do that is just like do a for loop over every single node and just DFS it if we haven't DFS'd it. And that way we'll reach every single node and we'll check every possible edge for a contradiction. Yeah. That's basically the solution. So I think that's all the details. I might have missed something. That, let me know if there's any questions. While I'm waiting for that, I can also just mention, instead of checking within your for loop, you could check at the end. So since all the edge conditions are really easy to check, they're just checking if some difference is true. You could just do the DFS and not actually worry about checking within that, and just at the end go over all your edges and check the differences, right? And if they're not, then you failed. And if they're all correct, you're good. Right. If I missed anything, I can just answer anyone else. Let me know, because I wasn't prepared to present this problem. But I think that's all I have.
Should be good, I think. That'll show up.
Yeah, it looks good to me.
Does Dallas have a problem there? Or did we have
I'll
results?
do F.
Yep. So just share your own screen. It's probably easier.
Yeah. Can you make my desktop co-host?
Yeah. Done.
Okay. All right, that's up now.
Yep.
Okay. So basically, the problem is Fred and Francis are hiding inside a rectangular pen. They're inside the pig's pen, which is rectangular area. Farmer Frank is coming, and Farmer Frank walks in a straight line, and at every point, he can see a certain radius around him. Is there a point inside the pig's pen that Fred and Francis can hide in, such that Farmer Frank can never see him? So if Fred and Francis are inside this pen, Farmer Frank could walk from here to inside the pen, or maybe he would walk from just outside the pen, or he can walk completely inside the pen. He can walk straight through the pen. It doesn't matter. He just, any 2 points, and he walks in a straight line between them. So let's consider where Farmer Frank can actually see on his path. So let's just not look at the pen for now. We'll just look at the path that Farmer Frank walks. So he'll walk a straight line. At every point on the line, he can see a circle around him of radius, whatever it is. Here, R, radius R. So at every point there's a circle. You should just be able to tell that this will draw out a rectangle on the sides. So this will just be a straight line. This will be a straight line. And the distance from the perpendicular distance from the path that Fred walks will be r. And then at the very ends, it'll be a semicircle of radius r. So this is the shape that it looks like. There is a special property about this shape. I'll change what I'm sharing. Right, so this shape is what is called a convex shape, although it's not a polygon because it has that curved, the semicircles at the ends. So what's special about a convex shape is that if you have a straight line from 2 points inside the shape, the entire line is inside the shape. So I have these 3 green lines. This one on the top left, one of the ends is outside, one of the ends is inside. This one on the very right, they're both outside. If they're both outside, that means the entire line is outside. And for this one down here, both of the ends are inside the shape, which means the entire line is inside. You can't erase that like that. And conversely, this is what is called a concave polygon. So it just doesn't have that convex property. So you can see I have a green line. Both of the endpoints are inside the shape, but when you draw the line between them, there is a section of it that's outside the shape. So because the shape is convex, a shape we have is convex, that makes things a lot easier for us when we try to put the paddock inside. So you can see if we try to fit the paddock inside a rectangle like this, either the entire paddock is inside the radius, or if it's not inside the radius, that means there's some line, one of the edges, that is not completely inside, and that means one of the corners is not completely inside because of the convex property. So now the problem becomes, how do we check if the corners are, like if any point is inside, because we only need to check it 4 times, 1 for each corner. So if you draw out just the shape, it's a bit misleading. We don't actually need to check if it's inside the shape per se. We just need to check the distance from this red line. So to do that, you basically you can just use a template. Computational geometry is something like 70–80% just knowing the templates. Otherwise, actually figuring it out in the contest is very time consuming. It's not always difficult, but it's very error prone and it can take a lot of time. But the gist of it is, if you know point line distance, you just draw the line that is perpendicular to the red line from any point. And the length of that line is your point line distance. For point segment distance, you have an extra check. Is the x values of the point you're checking between the 2 endpoints, or is the y values between the 2 endpoints? If either of those are true, then you can use the point line distance. Otherwise, you just use point distance from the endpoints and then take the smaller one. So for example, if I have this point up here, because it's outside of the interval, then we take the point distance to the endpoints, and then we just take the smaller one. So we would take the blue line in this case, and then we'd find the distance of that. And yeah, that's basically it. If you don't know how to do point line distance, if you haven't learned it in high school, it would be covered in first year under the topic vector projection. So you project this point onto this line, and that'll create the orthogonal projection, and then you can find the distance of that. But yeah, it is a lot easier because, especially in divisionals and regionals, you have unlimited paper. just print out a bunch of formulas from computational geometry and use that. In World Finals, you only have 25 pages, but divisional regionals, you have as much as you want. I think that's it. Unless, is I guess any other comments?
I think nothing from me.
Yeah, that's good.
All right, which problem should we look at now? Any what are people saying? Have a look at H. H isn't very interesting. Okay. Right, and who was M assigned to?
I'm happy with
You have to do M? Okay.
Yep. Right. M is called Jenga, but it basically has no resemblance to Jenga as far as I know, except that it has squares, I guess, which is an invention. So yeah, I think it's easiest with the diagrams in the form of this. So what you do is you have a grid, a 3x4 grid, and each cell in the grid has a point value. And you also have a width of your Jenga blocks. And what you're basically doing is just building a Jenga tower in this space from bottom to top or whatever, such that it's freestanding. So this one is a valid one in this case because it's freestanding, and you can see you can't do any better because you're only allowed to place one block per layer. So in each layer, you put a consecutive sequence of this number of blocks, which is called K, little k. Okay, so that one was pretty simple. I guess because it's small. Yeah, and the condition is that you can't have a floating block basically. So every single block has to share at least one cell with the block below, or each block placed in a row has to share at least one column with the block placed in the row below it. So even though it's not useful in this situation, you can't have something like this on any layer. So you can't have it there, you can't have it there. So if these two blocks were there, that would be banned, and if these two blocks were there, that would be banned. And also you can't run off the edge and whatever. So yeah, it's pretty well defined, I think, at this point. Yeah, are they positive? Yes, they happen to be positive. I guess that's makes some small changes to even think about it. Okay. Yeah, I guess I'll do this sample. So this sample is very interesting because you can't actually get all the biggest numbers, I guess. So I think the easiest way is to just try everything. So you can kind of try everything for the bottom layer. So the bottom layer, you're either going to do 5, 1, 1, 2, 2, 2. And if you do whatever you do, you're going to want to pick this and this for the top two, because you can, because they're always going to be on top of it, regardless of which bottom layer you pick. So that means we should just pick the biggest bottom layer, which is that one. And so that is the best solution. And yeah, so the thing makes you actually output the construction rather than just the number. Sometimes it would just be the number, but in this case, you output the construction. And yeah, if there's multiple solutions, you can output the construction. Okay, last case is completely useless because it is useless because wherever you place the box, they'll be equal, and wherever you place the box, they'll get scored the same number of points. So any output that is a valid arrangement of Jenga blocks would be accepted. So it doesn't matter if they're in the right position or the left position, the left two or the right two. It's useless. Yeah, okay. So I guess this one proves the point better that you can't have stuff. So you couldn't have x dot x because this one doesn't overlap with that. Okay. So yeah, these samples aren't very interesting, but I guess the one that was not obvious immediately what the answer was this one. Perhaps it's not immediately obvious. So what we did in that case was we checked every single bottom layout and see what we could do with the next set. And in fact, the observation is, if you can even call an observation, is when you're choosing where to put your block, all you care about is the block beneath. You don't care about anything you've done before that. And that motivates the DP solution. Or that motivates using DP. So yeah. So the fact that we only care about the block below us means that we can split this into subproblems, and the subproblem is, or the state is, what is the last block we placed? So we build from bottom to top and we say, what is the last block we placed? And we say, if our last block placed was here, what is the maximum score we could have right now? There's a few different ways to set it up, which will ultimately be symmetric, or do the same thing, but just with different setups. So my setup is going to be, if you build up to here, if your last block is placed here, what is the biggest your total score can be? So to make that state more precise, we need to clarify what last block placement is. So you can identify it in a few ways, but an easier way is to just identify what's the left position of the last block we placed. In particular, what's its row and what's its column. So say we built some stuff here, we don't actually care because we can't alter that anymore. And say that our last block built is going to be here. We care about what we placed there, I guess, because that's how the difference will end up. So let's say our last block built was there. You know what? I'm going to change my reference or my state. My state is going to be if we last placed this block, what is the maximum score we can get building from now on? So say our last block was placed here. What is the maximum score we can get building only above it? Okay. So our last block placed will be specified by a row and a column. So DP of row and column. If our last block had the left position at coordinates RC, so that means it's the leftmost position of its block, what is the largest score we could get? Largest score we could get with remaining blocks. So yeah, this one's probably a bit more intuitive, which is why I changed it, but yeah, hopefully that, I guess, provided evidence that you can set it up in many ways. I just filled up my entire iPad screen, so that is not very useful. I guess I'll have to delete it now. Yeah, remember that, I guess. So the recurrence is pretty much an implementation detail. So it's basically just implement the problem, because the problem specifies exactly how the loops can work. So it's easy to see with the diagram, but you can also do it with all the equalities and inequalities and checks that you want to do. But if your last block was placed here and your width is like that, then you can place it like there. Let's clarify the width. Say each of these is that. And There's like a thing there. Now, if so, the width is 3 and the total width of the whole column is 7. So in this case, you can put one there, put one there, one there. So this is just the next row, but I have to draw them into each other because it's visible. You can put it there, you can put it there. You can't put it there because that would run off the end of the row. You're not allowed to do that. So basically what you have to do is for each last position placed, your next position can be anywhere that is. So the conditions you have are, you have your right edge must be to the right of the left edge of the previous one. Your left edge must be to the left of the right edge, so it couldn't be there. And your right edge of the new one can't be off the end of the thing, off the end of the board, and your left one can't be off the end of the board. So if you just check all those 4 conditions, then you get four inequalities that must be satisfied in order for a valid state transition. And yeah, in this case, you can just do it really slowly. You can just add them all up together. Sorry, not add them all together. You can take the max of all your options in order to compute from one row or from one state what's the best option. Okay. So hopefully, yeah, those 4 inequalities make sense, because that really is just dp plus understanding how the blocks can be placed. Is there anything else? I feel like it was. We're just backtracking. We have to do. Yeah. So I guess there's at least 2 things left. So one thing is our state was if our last block was placed here. So what's our base case? Well, our base case you can actually have many base cases. So your base case could be wherever you put the block on the bottom row. So it depends on your set. We could probably do it without multiple base cases if you set it up differently. But in this case, you can just say, what is the best score if I put my first block there? And how about if I put it here? And how about if I put it here? And so on. And just take the maximum of it, because you'll eventually cover it. And that will only take a small amount of time. Okay, yeah. So another detail is how to print the construction. So far, I've only talked about how to get the maximum. One other thing. So yeah. So in order to actually print the grid, you need to keep track of which moves are actually optimal each time. So an easy way to do this, if you haven't seen it before, is for each state, you not only store like the maximum score you can get, but you store the best move from that position. So if you remember, state was last block placed. It's pretty intuitive in this case. So you store as your value, best score. This is what I wrote up before, filling the whole page. And you add another array, move or something, which is best move. And that is basically just which column you should place it in, because the rows are already specified, but you can specify which row as well. And yeah, so basically what you do, once you've set up all of these things, well, once you've set up the DP, you can compute all these values. That's just a classic DP. And once you have the move array, what you do, or move thing, is so you can find the first move pretty easily. You just pick it from whichever one's the biggest DP, and then from there, you place it there, and you move to the state that is best. So you take that move. So yeah. So once you've placed the first thing, and you pick that one so it was best, you say, what is the move that I set when I was picking the state, and that move was defined by whichever value was best, and say it was there. So then you put it there, and so on. So basically, it's backtracking. So you go through the moves such that you always pick the best option at any given time, and in that way you reach the best setup. And that's how you output the final thing. Okay. Yeah, I think, yeah, I don't know how much detail to go into that because you could go into more detail, but I think I'll leave it there for the backtracking moves. Yeah, I think that's about it. Sorry if that was a bit disorganized, but yeah, feel free to ask questions if any parts of clarification. And while you're doing that, if you're interested, you can solve this problem faster. I should mention time complexity. I think that's what I was forgetting about. So I'll talk about time complexity now. So how many states do you have in your DP? Yeah, I think we're just assuming that you know what DP is at this point. But anyway, so there's how many states do you have? Well, your state was where you last placed your block, and it's about R times C. A lot of states are, well, not a lot, but some states will be invalid because they'll run off the end, but it will be order R times C. I guess you can clarify, you can specify it precisely, it'd be like order R times C minus K. Time complexity of this DP, order R times C minus K. And I guess that is order RC. Use the notation as it the notation. Yeah. And so that is the number of states. But if you remember, I said you could just do the recurrence really quickly. You can just check every single thing. And you can do this with many different time complexities. If you just for every state compute, if you loop over every single place you can put the next block, then there's order C places you can put the next block. And you actually want, you also have to compute how much that will score. So you have to compute the sum. So order C times order C again, because you have to sum over potentially up to C blocks, or up to K, exactly K, but it could be up to C. So let's clarify. This gives me a whiteboard space. So that one comes from the state. That one comes from options, number of options. That one comes from computing score of each option. Okay, so we have order RC cubed. RC cubed. It's a horrible time complexity, but is it good enough for this problem? Probably. 50 to the 4, what's that? 50 to the 4.
50 to the 4 is small enough.
Small enough. Yeah, that's the exact value. It's small enough. Yeah. Now you could, I'll just mention it, because why not? You can do this one faster using prefix sums. Not even 2D prefix sums, just 1D prefix sum, one for each row. And if you're really feeling fancy, you can do that one faster if you want, because this is a range query. So if you've computed everything in the row below, then you're actually just querying a range of valid things. Depends exactly how you set it up. So you can do that using any range query thing, but since they're all fixed range, you can do the sliding window max range, and you can search it up because it is very well documented online. So sliding window range, and that is going to be order C pre-computation. Wait, yeah, order C pre-computation per row, and order 1 queries. I don't know why I've rectangled that so many times, but yeah. So in that way, you can actually do this problem in order RC, but you absolutely don't need to for this problem. Yeah, okay. We've gone on for too long, but anyway, that's it. Okay. So any next problem with this since no one's saying anything?
I'll go over K quickly. All right. Pascal the chameleon is exploring a corn maze. Corn maze is a square grid. Some of the cells are blocked off. Pascal can only travel through cells that are cleared out. He can move up, down, left, right, not diagonally. Some of the cleared out cells contain candies. This is pretty important. The cells that contain candies do count as cleared out cells. There are 9 pieces of candy, each labeled 1 to 9. So there's exactly 9 pieces, 1 of each number. There can't be multiple of each number of candy. And he must eat the candies in increasing order. Every second, Pascal can either move or eat a candy, but not both. As Pascal is a chameleon, he has a long tongue. He can eat a candy at most K cells away in a straight line in one of the 4 cardinal directions. So his tongue can't like whip around a block or something. It has to go in a straight line. His tongue is able to pass through candy cells. We want to find how long it would take Pascal to eat all the candies. So let's just go through the sample inputs first. First one, grid is 2 by 5, and Pascal can eat candies 1 cell away. So what he can do here is eat candy 1, then move to position of candy 1, eat candy 2, move to position of candy 2. So that takes 4 moves because it takes 1 move to eat candy 1, then 1 move to that position, then 1 move to eat candy 2, then 1 move to move that position. Same thing candy 3. So that's 6 moves. For candy 4, he eats candy 4, so that's 7 moves, but he doesn't actually need to move there. So he only has 7 moves. And then he goes down to candy 8, but he can't eat it yet. Back left to candy 7, back left to candy 6. So that's 10 moves, I think. And at candy 6, he can eat candy 5. That'll 11 moves. He can eat candy 6 because he's already on it. So this 1 doesn't mean he has to eat it 1 distance away. It means at most 1 distance away. So he can't eat candy 6 when he's on it. So that's, I lost count, but 12, I think. And then he eats candy 7 from there. He moves to candy 7. 14 moves. He eats candy 8, moves to candy 8. That's 16 moves. He eats candy 9 and he's done. He doesn't have to move to candy 9. So that's the 17 moves. Sample input 2. He starts from S, moves to the right once, and then goes all the way. No, he moves to the right, eats candy 1. Or he could eat candy 1 straight from the start and then move to the right. It doesn't matter. 2 moves, he gets the same position. And with the same number of candies eaten. So, and then he moves all the way down. So that'll be 1 move to move there, 1 move to eat the candy, and then 2 moves down. So that's 4 moves. Then he can eat candy 2, 5 moves. And because the distance is now 2 and not 1, he can eat candy 3 from there as well without moving. So that's 6 moves, and he's still in this position here. And then he can eat candy 4, that's his 7th move. He can eat candy 5, that's his 8th move. And then he has to move back up to reach candy 6. So 9, 10, 11. And then he can eat candy 6, his 12th move, eat candy 7, 13th, eat candy 8, 14th, and eat candy 9, 15th, and he's done. So that's 15 moves. And then this last sample input, he starts here. He can eat at most 10 units away, and all the candies are 10 or less units away, so he can just sit here and eat all of them. And because there's 9 candies, it takes 9 moves. And remember that his tongue can go through candies he hasn't eaten yet without actually eating them. So that's why he can reach candy 1 without, even though there's other candies blocking him. So that is all the sample inputs. So I kind of hinted at something there. It doesn't matter how he moves. If he gets to the same position after having eaten the same number of candies. So what we can do is pretend there's 9 copies of the grid. So he will be, Pascal will be at this copy at the start. He has eaten 0 candies so far. After he eats a candy, he moves to this next copy in the same position he was at before. So now he's eaten one candy. Then he moves to this one. Now he's eaten 2 candies, and so on and so forth. And this last one will be after eating 8 candies. Oops. And then once he eats the 9th candy, he moves off the grid, and that's when he's done. So this is just conceptually. Don't actually store the grid 9 times. You don't need to. You just kind of keep track of which copy of the grid you're in when you're moving through, when you're moving Pascal through. So as I noted before, it's never better to be at a position in a specific grid with more moves than necessary. So if you can get to position IJ in the grid marked 4 in 20 moves, that's always worse than getting to position IJ in the grid marked 4 in 19 moves. But note that this isn't related to how you the number of moves to get to position IJ in any of the other grids. It's only IJ in this grid. So what we can do is do a breadth first search, but actually involve which grid number we're in that search. So if you don't know what a breadth first search is, basically you have at a certain position, you have a number of moves you can make. You put all of those moves into a queue if you haven't seen them before, and then you pop your next move off the queue. And what this does is it ensures that when you pop it off the queue, you have everything in increasing order of distance. So you'll always look at everything that's 1 move away from the start before you look at everything that's 2 moves away from the start. And it'll ensure that when you pop something off, it'll be the minimum distance it can be at. So you'll never run into this position where you're at IJ in 20 moves instead of 19 moves. You'll always encounter the IJ in 19 moves first. So yeah, basically it's just a BFS, except normally BFS, when you're on the grid, you move up, down, left, right in 1 move. In this case, you can either move up, down, left, right in the same copy of the grid, or you can move to the next grid at the same position, and that takes 1 move as well. So to check if you can actually move to the next grid, if you try to just check if you can eat a candy at each position, that's too slow because I won't share my screen again, but if you bring up the questions, R and C are up to 200,000. So you could be potentially checking 200,000 spaces for every position in the grid, for every candy number in the grid. So like each copy of the grid. That is just too slow, 200,000 times 200,000 times 9. So what we can do instead is we pre-process the candies. So we have at the very start, we have a candy here in the middle, and we just go up, down, left, right from it until we meet one of the blocks, so we reach the edge. And we mark everything. In this straight lines as I can eat candy C from here. I can eat candy C from here. I can eat candy C from here. And for everything outside of these straight lines, I cannot eat candy C. And then what you just do is every time you're at a position to check if you can eat candy C, you just look this up in the in your table, and instead of checking all of the cardinal directions for each position. And that is basically it. So it's not a it's not a difficult problem once you get the idea of it. I guess thinking up how to apply the different number of candies to the state is what makes this difficult. Also, this pre-processing, I guess, might not come naturally to some people.
Okay. It's almost 6 o'clock, so unless there's any more comment from either you or Isaiah or any questions, I think we'll finish up.
Yeah, all good from here from me.
All good for me too.
Okay. Any comments from anyone who's still here?
Also, if people actually care about the problems, because I think there's still some stuff on the poll that people had voted that we haven't covered. We can do like a 2-minute explanation.
Yeah, if you are keen to hear about other problems, we can do them a bit over if there's demand for them.
But yeah, we should probably do it quickly as well. I think most of the ones left are we should explain pretty quickly.
Last chance to speak up if you want anything. All right, I'm going to assume there isn't demand for anything. Thanks everyone for coming. That's it then. All right, I'll stop the recording.